Hi everyone and welcome back to our YouTube channel. In this lecture, I will show you another method that is used to compute the determinant of a given square matrix. And this method is called the Laplace or cofactor expansion. And in order to understand how this method works, we need to learn about some terminology called minor and cofactor. So let's first start with the definition of minor and cofactor and try to understand what they are and how we will find these values. Okay, and here's the definition for the minor. A minor of an element, the minor of an element Aij in a matrix actually is the determinant of the submatrix that remains after removing the ith row and jth column from the original matrix. Then what this means? Let's work on this definition. Okay. Now, suppose we are given a matrix, and let's see how we understand the definition. Okay, let's say 1, 2, 4, and say minus 1, 3, 5, and let's say 0, 1, 2. Suppose this is the matrix given to us. Alright, and we know what a minor is. And if I want to find the minor of an element in this matrix, for instance, suppose that I want to find the minor of this element I just circled in black, which is the 2, 2 component of this matrix. And in other words, a 2, 2 component. Okay, now suppose I choose this value. Okay, and then what is the minor? If I want to show the minor in capital M, okay, we are looking for the minor for this entry in this matrix, in the square matrix. So we're looking for M22. And this component is actually right at the intersection of the second row and the second column. So what the definition says is, okay, so we need to remove or delete the row and column of this corresponding entry from the original matrix. And since this element lies right at the intersection of the second row and the second column, then I need to remove both the second row and second column. And then I will rewrite what is left behind after removing this element without changing the order of the elements given in that matrix. So if I remove the second column and the second row, let me use another color. So if I remove the second column and if I delete the second row, then what is left behind? From top to bottom and from left hand side to the right hand side, I don't change any order of the elements in this given original matrix. So I just write the entries left behind. So this is 1, 4, 0, and 2, right? This is what is left behind. So this is the remaining entries. And the determinant of this matrix, which is actually now a 2 by 2 matrix, is called the minor of the corresponding entry in that original matrix. And we know how to compute the determinant in many different ways. We have a 2 by 2 matrix, and then by multiplying these entries, 1 times 2 is equal to 2 minus 0 times 4 is equal to 0, and 2 minus 0 is equal to 2. So the minor of the 2, 2 component of this matrix is equal to 2. So the minor of any element in this matrix is the determinant of the submatrix that remains after deleting the ith row and jth column from the original matrix. Since we are looking for the 2, 2 component of this matrix, then I just deleted the second row and the second column, and I write all the elements left behind after this deletion process. Okay, now let's find another one. Okay, now suppose I want to find the minor 1, 3. Okay, so suppose I want to find now M13. So what should I do now? Alright, now This time, what should I do? Let's delete back to avoid confusion. Okay. Now, suppose I want to find n13, so the minor of 1, 3. This means that now, what is the component of this matrix that lies at the intersection of the first row and the third column, right? This is 4. So, I need to delete the row and column that includes this entry. And this means that I delete the first row and I also delete the third column. Alright? So what is left behind? Without changing any order for the elements that remains, I just write the remaining ones. So what is remaining here? So these values that I circled in red are those that are left behind. So I just put them in the determinant: -1, 3, 0, and 1. So the value of this determinant is the minor of the 1, 3 component of this matrix. So -1 times 1 is equal to -1, and -0, and it's equal to -1. Alright. And if you notice that after deleting one row and one column, now if we have an n by n matrix in the beginning, then for the minors we have an n-1 by n-1 matrix, right? So we decrease the size by 1 in each direction for both rows and columns. Okay, now in this example I have a 3 by 3 matrix, right? So when I want to find any minor in this matrix, then I will compute the determinants of size 2 by 2. That's how it works. Okay, this is the definition of minor, guys. And now, another important definition. And this is called the cofactor of an element. And the definition of cofactor actually depends on finding the minors and then multiplying it by -1 to the power of I plus j. And here is the definition of cofactor. Let's first look into that. And the cofactor of an element aij, and again aij is just any entry in the matrix, in the original matrix. And if we denote cofactor as cij, then cofactor is computed by using this formula. So for instance, if I want to find cofactor 1, 3, then what should I do? Well, first of all, I need to find the minor of that element, right? mij corresponds to the minor of that entry. And then what I need to do is just, I need to multiply that value by -1 to the power of I plus j. And here, I is the row number and j is the column number, right? They are just the index values. So, if I want to find the cofactor 1, 3, then what is the value of I and j? And here, I is equal to 1, right? Because it is the row number. And j is equal to 3, right? Because j is the column number. So just be aware of that. Okay, now let's compute the cofactor of 1, 3. So actually, above in the example, I already computed the minor of that entry. And what should I do? What is left behind is, I just need to multiply it by -1 to the power of I plus j. And I is equal to 1. And j is equal to what? J is equal to 3, right? So, times the determinant. And I found the determinant -1. So, just multiply it by -1. So, what I have here? So, this is -1. And this is +1, right? Because the power here is an even number. And when the power of -1 is an even number, then this is equal to +1, right? So, -1 times +1 is equal to -1. So, this is how the cofactor definition works. So, cofactor and minors are actually any real numbers that are found by using their definitions, right? So, this is how it works. And having learned that, now we know what minor is, what cofactor is, and now we can explain what Laplace expansion method or cofactor expansion method is. So I can actually interchangeably use this method by saying Laplace or cofactor expansion method. These are the same, so no difference. Okay, and here's how the Laplace expansion method works. And the Laplace expansion method actually is another method to compute the determinant of a square matrix, but this time using minors and cofactors. We have just learned how to find the minors of cofactors of any given square matrix. And then after finding them, the rest would be just to apply the cofactor method to find the determinant. And how it works. Let's see what is the definition of this method. Okay, given a square matrix A, and let's show the components of this matrix A as aij's, then the determinant of A can be calculated by expanding along any row or any column using the following formula. Suppose we expand this matrix along row I, then our formula works in this way. So if you want to find the determinant of A, and suppose I is equal to 1. So what this means? When I take the value of I is equal to 1, then I expand along the first row. And I will use this summation formula. This means actually what I do is when I put the value I is equal to 1 in the summation formula, this is A1j times C1j, right? So over the summations of j, and j is the index, j is the column number, right? It starts with the first column and ends with the n column if we have an n by n matrix. And when we know the size of the matrix, then we just put the value of n as it is. If we have a 3 by 3 matrix, then n is equal to 3. Okay, then this means we actually multiply the entry in that matrix with its corresponding cofactor. And that's how we expand along row I, right? So if we write this formula, okay, and let me put it that way, right? If we have Aij, Cij. And by the way, we can select any row or any column that wouldn't change the value of determinant. The determinant value would be the same, regardless of which row or which column you have chosen to compute the determinant, because we are trying to find the determinant of the same matrix. So when we expand the summation, then we have, well, A1, 1, C, 1, 1, and then when j is equal to 2, then what we have? Then we have A1, 2, C1, 2, and it goes all the way up to the last cofactor, so plus A1n up to the last column, C1n. Alright, now Aij values actually are the components of the original matrix, where Cij values are the cofactor values of the corresponding entries. So we multiply them and take the summation. That's it. And this is how it works. And actually, I expand along the first row. If I take A is equal to 2, then the only thing that changed here is that we take the value of I equal to 2. And we compute the determinant by using the second row. And if I take the nth row, then I is equal to n. So the only change. But the value of determinant is the same, regardless of our choice of rows or columns. And if I want to do the same thing for the columns. In other words, if I want to expand along column J, then what would be changing? So only the index would be changed, right? Because this time, right, we expand with respect to a column, then what is changing is the number of rows, right? So the index in the summation formula would be from I is equal to 1 to n, where n is the number of rows. And so I just pick a column to expand. So if I write this formula again, there will be no change in the formula. But what is changing this time? We selected a j value. So if I select j is equal to 1, then this means we expand along the first column, right? I can again select any column as well. So this is, if I take the j is equal to 1, then what I have? So a11, c11, right? And then a21, and c21, and all the way up to the last row, right? So nth row, an1 and cn1. And what has changed? Well, if you look at this summation formulas in the one above, I expand my matrix. In other words, I compute the determinant by expanding along a row. But in the below one, I expand along any column J. So if you notice, A11, A12, and A1n are the entries in the same row, which is the first row in this case. And A11, A21, and AN1 actually are the entries in the first column in this case. And again, I can choose any row or column to apply this cofactor expansion technique. That's why actually it's called a cofactor expansion. Because if you see, we multiply the entries by their corresponding cofactors and then take the summation. So we kind of expand this definition as an algebraic sum, right? Because the cofactors are any real values and components of the matrix are any real values. So we have again a real value, right? So that is something which should be correct. So because we know that what is the determinant? So determinant is actually, right? Determinant is actually considered a function. What kind of a function is that? Well, we take a n by n matrix, right? So we are given a square matrix of size n by n, right? And move it to its determinant, where determinant is any real value. So this is kind of a function, right? We can think it. Our domain set here are actually the set of all square matrices, and our range set is the set of real numbers, right? So we can consider it as a function like this. All right then, now, having understood what a minor is, what a cofactor is, how can we find the determinant of a given square matrix by using cofactor expansion? Now let's get back to our main point. Let's give an example and see how we can apply this formula. Okay, here's the example. Let's first define a square matrix. Okay, now say 1, 3, 0, -1, 4, 3, and 2, 1, 3. All right. Now let's say this is the matrix given to us. This is our original matrix. Say it A. And let's find its determinant by using cofactor expansion method. Okay. What's the determinant value? Okay. Now, let's solve this problem. Alright guys, I will choose any row or any column. That doesn't matter at all. Suppose I choose the first row. Then what should I do? Okay. And here's the determinant. Okay. I just apply the formula we just have discussed about. So suppose I choose the first row. Okay. So select, or well, say it expand. Okay. Expand along the first row. Okay. Expand along the first row. Let's see how it works. And what the definition says, I will apply the summation formula. If I choose the first row, then here's the definition. We have A11. So because, let's use another color. So this is the first row, right? This is the first row. Okay. The one that I just draw in a red line. You see, this is the first row. So I will use those elements. Okay, A11 times C11, the corresponding cofactor. And then, since we have a 3×3, you see, we have a 3×3 matrix here. So our original matrix is of size 3×3. So I have 3 terms in the summation formula. And since I expanded along the first row, then I use the elements in the first row, which is 1, 1, 1, 2 component and 1, 3 component, right? And their corresponding cofactors as well. So A1, 3 times C1, 3. Okay. Now, let's move one step forward. I know the value, right? What is the value of A11? Well, look at here. It is 1. So 1 times, what is the value of C11? Well, we need to find it, right? So we need to find C11. How should I do that? Okay, now, the value of, well, the cofactor value of C11 is equal to, actually, what is the value of cofactor? This is -1 to the power of I plus j, and for the first component we have I is equal to 1 and j is equal to 1, so the power is an even number. So -1 to the power of 2 is +1, right? So no change on the sign. This is +1 times the minor. And how we can find the minor? Well, since this is the 1, 1 component, I delete the first row and first column and write the remaining elements in the same order. And what is left behind here is the elements I just circled in red, as you see. Okay, I just write them here. So find the determinant of this 2×2 matrix, 3, 4, 3 and 1, 3, right? So what is the value now? So 1 times, okay, we know how to find the determinant of a 2×2 matrix. It's very easy, right? So this is 4 times 3 minus 1 times 3. So 12 minus 3 is equal to 9 times 1 is again a 9, right? So this is equal to 9. So we found first cofactor. So this is 9. Okay. 1 times 9. All right. Plus. Okay, let's continue. Okay, now the second term, A12. So what's the value of A12 here? So we see that A12 is equal to 3, right? So 3 times, and what is the cofactor for 1, 2? So it is the element or the entry that lies at the intersection of the first row and second column. So I just delete the first row and second column and then rewrite all the remaining elements without changing their order in the original matrix. So what is left behind is, actually, let's put it here, the determinant we should compute minus 1, 3, 2, and 3, right? From top to bottom and from left hand side to the right hand side without changing the order. I just put the remaining elements as they are and compute the determinant. And don't forget one more thing. We also need to multiply it by minus 1 to the power of I plus j. And here is I is equal to 1 and j is equal to 2. So minus 1 to the power of 3. So this is minus 1, right? Because this is an odd number. So the power of minus 1. And well, if the power of minus 1 is an odd number, then it's equal to minus 1. So what's the determinant of this matrix? Minus 3 times 6, it's equal to minus 9, and times minus 1, right? So it is plus 9. So we have one more 9 here. So I just put it here. Okay. Plus, now the last term, A13. Well, the good news is here, if you notice that, guys, what is the value of A13? Well, it is 0, right? Well, actually, that's why I choose this row, because it includes at least one 0. And as you remember, more 0 values means more easier computation. So that's the reason actually why I choose the first row, because it has at least one 0. And if I had a row which has much more zeros, then I would have chosen that row or that column, because it would make my computational cost decreasing, right? So my computational cost would be decreased if I choose the rows or columns which have more zeros. So I don't need to even compute the cofactor here, because 0 times some value is equal to 0, right? So the third term is equal to 0. And then what is the determinant? This is 27, 3 times 9. And this is 9. So we have 36. All right. Now we found the determinant. I just expand along the first row and found the determinant by using cofactor expansion method. And I can do the same thing for any row or column. For instance, I could have chosen the third column, for instance, right? So I could have also chosen the second column. But the easiest strategy is to choose the one row or column which has more zeros. Well, if none of them has zeros, then just select either of them. That doesn't matter, because it would be pretty much the same computational cost.